Hey, IB Pre-Calculus. Welcome back. In this lesson, we're going to be building on some of the concepts that we reviewed and worked with last week. We did a lot of work with graphing sine and cosine and writing equations and seeing the impact of the amplitude and, right, so the amplitude, the period, the phase shift, the sinusoidal axis, and how you write these equations, and how one is just a horizontal translation or a phase shift of the other, and how you can write multiple equations for the same situation. And so in this lesson, we're going to build on that, and we're going to look at applications of sine and cosine. So we'll look at some scenarios or situations that vary sinusoidally, that follow a sinusoidal pattern, and write models and analyze those situations and draw conclusions and make predictions. So throughout this video, you might want to have, there's actually a note sheet that's linked on the page. You might want to have that out because we're going to be going through those examples, and so it might be nice not to necessarily have to write them all down as we go through this. And in addition to that, here is your part 1 homework that goes along with this lesson, and I really encourage you, after you go ahead and watch this, to try some of these problems to get some practice and see what questions you might have early on in this week. So with that being said, let's get started. Before we go into some actual models of this, let's look at some situations that do vary sinusoidally. And maybe you can think of some before I even show this list. My list is not comprehensive. There are more than just this. I just pulled out a few that I thought of and we would work with. So you might be able to think of more, which is awesome. So some things that vary sinusoidally are change in temperature over time, right? So maybe over the course of a year, and you can think about how that graph or that situation might be different in, I don't know, different parts of this country, or in different countries, or on different sides of the globe. Like, what would the graph look like if you're talking about the variation from January of one year back to January of that year, or I'm sorry, January of the next year? Hours of daylight over time, right? Like right now, the days are getting really short, but at some point we get to the shortest day. Isn't that the winter solstice? And then, I hope that's right. And then then the days start getting longer, right? And we get to another day, the summer solstice, and we get to the longest day. And then the days get shorter again, right? So that's going to vary. You're going to get to your maximum and your minimum, and it's going to bounce back and forth or oscillate between the two. Ocean wave height, so like high tide and low tide, right? Over time, maybe like in a day, how many times do you get to high tide, low tide, high tide, right? Like it's bouncing back and forth. You can think about what the period is. Sound waves, biorhythm waves, electrical currents, Ferris wheels and roller coasters, right? Like it could be like your height on a Ferris wheel. Tsunamis and tidal waves. They're not all going to look the same, but they vary sinusoidally. Earthquakes, wheels, trampolines, and swings. So again, not comprehensive. I'm sure you can find some more, but you're more than welcome to maybe look at some of these and see how they do vary sinusoidally, or look at some situations with it. I encourage that. So let's get started with example 1. I'm actually going to make my screen smaller because I want to have my calculator with me as well. Ooh. I don't want to scroll too much, so I'll grab my calculator. Awesome. Okay, so in this problem, and so for most of these, like I'm going to read through the situation and see the key pieces of information, and then I really want to write a model, meaning I want to write an equation. Okay? Those are really the ways that I want to approach this, that I can make conclusions. So on January 1st, 2008, in Ocean City, Maryland, oh, I'm sorry, I skipped a line. The first high tide occurred at 2:11 a.m. At that time, the depth of the water was 1.9. So high tide at 2:11 is 1.9 meters. The first low tide occurred at 8:14 a.m. at a height of 0.4 meters. Okay, so we want to approximate the depth of the water at 6 a.m. and at 1 p.m. What was the first time when the water was 1 meter deep? So I'm going to go ahead and I want to write a model for this situation. I'm going to write it over here. So I'm going to think through like what's happening here. The first piece of information that I'm given is high tide, right? And so like this point right here, this happens at 2:11 a.m. and it's 1.9 meters. Some hours later, we get to low tide, right? And that's at 8:14 a.m. and that's 0.4 meters. Right? So then after low tide, it's going to go back up and we're going to hit high tide. So we want to figure out what's exactly happening here. Right? So 2:11 to 8:14 is 6 hours and 3 minutes. So after another 6 hours and 3 minutes, we're going to get to high tide again, right? That's going to be the approximation of this. So that's going to be at 14, which is, I'll write it, 14:17. And we're going to get to 1.9, right? 14:17, what is that? 2 o'clock, 2:17 p.m. is what's really happening then. So from this information now that I have, I can figure out what's the sinusoidal axis, what's the period, what's the amplitude, would it be sine and cosine based off of how I just wrote this? So that's the piece of information that I want to go ahead and figure out. So I'm going to start with the period. So it's from 2:11 to 2:17. That's what? 12 hours and 6 minutes. It's going to be a little bit hard to work with the period when I'm dealing with both hours and minutes. So I'm going to go ahead and actually just convert this to minutes, right? So I'm going to take and go 12 times 60. Oh my goodness, it doesn't love me. So I get to 726 minutes is going to be my period. That's how long it takes it to go from high tide back to high tide. So I'm working in minutes. And so I think I'll write that up here because I think that's a pretty important piece of information. So I know I'm going to be dealing with cosine. I'll come back to what A is, what my amplitude is. I know I'll have a positive over here. I'll have cosine. And then this is the period. So to figure out B, I need to do 2 pi over the period to figure out what B is. Right? So if I go ahead and do 2 pi over the period, I'm going to leave the pi. So I just want to know what's 2 over 726 is 1 over 363. So I've got pi over 363. X, what's my phase shift? Well, I'm starting it at 2:11. Don't forget that I'm working in minutes. So I'm going to go ahead and I want to convert this to minutes, right? So this would be 131 minutes. So my phase shift, I should have minus 131. And then I want to shift gears and I want to talk about, I want to look at the Y values, right? The minimum and the maximum, so I can figure out both the amplitude and the midline, the sinusoidal axis. So I'm going to go ahead and average those to figure out what's halfway between them. Right, so if I go ahead and average them, what do I get? 1.15. So that would be, oh gosh, that would be my midline. That would be my sinusoidal axis, right? Right here would be y equals 1.15. So I want to figure out from the sinusoidal axis to the top, how far is that? Right, so I could go ahead and do something like 1.9 minus 1.15 to get 0.75. Right, and so I'm just going to write 3/4 based off how much room I left myself. So that I could figure it out that way. The other way I could also do it is I could go ahead and figure out the difference between them and divide it in half, right? Like what's the range and what's half of the range is really what I'm looking for in that value, right? So amazing. Now I have a model. I can make some of these predictions. So what was the depth at 6 a.m.? Well, don't forget that I'm working in minutes, so I need to convert that, right? I need to go ahead and do 6 times 60. Unclear why I'm going to use a calculator. 360 minutes. 1 p.m. is what? 13. So I need to go ahead and do 13 times 6. 7 times 60, sorry. 780 minutes. So like it's really my X value, my independent variable is hours after midnight or after 12 a.m. on January 1, 2008. That's really what I'm looking at here for when I'm substituting it. So I'm going to go ahead and plug in these values, right? So I've got 3/4. Excuse me. 3/4 cosine. Oh, I need to make sure I'm in radians. Yep, okay. I worked in radians. If you worked in degrees, you got to make sure you're in degrees. Pi over 363. X, in the place of X, I'm putting this time 360. Minus 131. Close parentheses, plus 1.15. Right, so the approximate depth at 6 a.m. would be 0.85 meters. And think about, like, does that make sense? Okay, so like this was 2 a.m., this was 8 a.m., we're somewhere about halfway between them. Oh, that makes sense, right? Like I'm a little bit below the sinusoidal axis. Right? So I can go ahead and let's do the other one. So 3/4 cosine of pi over 363, parentheses, what am I at, 780, minus 131, close parentheses, plus 1.15. So I've got over here about 1.74 meters. Right, if this is just one decimal place, I might want to change this to 0.9 meters and this one to 1.7 meters so it's consistent. That's how it's being measured. Right? So, and then does that make sense? So I'm like right before I get to the highest point, which makes sense, right? I'm a little bit before 2:17 p.m. It's like an hour, 17 minutes before that. So I'm also going to go ahead right now and I'm going to actually put my model into y equals. So I've got 3/4 x minus 131. And before I graph it, I'm going to go ahead and change the window because we can think through what the situation is, right? So if remember my x is in minutes. So I'm going to go I'll go from 0 to, this is 780, I'll go to 800, right? And then my y, I'll go from 0 to 3, right? If the maximum is 1.9, actually, I don't even know if I need to go that high up. I'll go to 2.5. Then I'll go ahead and graph it. As you can see, right? We can see that one cycle. Maybe I'll change the window even more. Maybe I'll make this so you can see a little bit more of it. Right, so I could also go ahead and look at the table of values, or I could do second trace value, and I'm looking for 780. Let's go ahead and 780, enter. We can see what the output is, right? So using the model. So in this second one over here, when it's asking you what's the first time that we get to 1 meter, that it's 1 meter deep, it happens more than once, right? It happens sinusoidally. So you want to think like in this, like from this starting point, where's the first time I get to 1 meter? So like on the way down, right? So mathematically, what I'm doing is I'm doing 1 equals to 3/4 cosine of pi over 363 x minus 131 plus 1.15, right? So mathematically, I could go ahead and say I'm going to do 1 minus 1.15 and then divide by 3/4 or multiply by 4/3. And then I would have cosine by itself. So I'd have to do the cosine inverse of what I just got. And then I'd have to multiply by 363 over pi, right? Like we have the algebra skills for this. And then I'd have to add 131, right? So I would get that x equals to 335.766, right? And so this is minutes. This is minutes after midnight. So then you could think through, well, how many hours is that? Let's go ahead and divide it by 60, right? So this is going to be at 5. I'll then get rid of the 5. Let's convert this to minutes. So times 6. No. Yeah, times 60. So at about 5:36 a.m. is when it would get to that. Right? I could also do this graphically. I could go ahead into y equals, I've already graphed it, and then graph another one where I'm graphing the line y equals 1. And I want to find their point of intersection. So you can see like this is high tide. It drops down right here. It's the first time it gets to 1. This would be the second time. So I could go ahead to second trace and find that point of intersection. Right? I can get my cursor over that point of intersection, if it would be so kind as to go over there. And I could calculate it or find it. So the point of intersection is 335.662. Isn't that what I said? And then we can convert, that's minutes. I converted it to an actual time. Right? If it asked you for the second one, you could go ahead then to the second part of the curve. If it asked you for a third one, you could zoom out more on this. You could change the window to see more of the cycle. Awesome. Let's go ahead and let's look at the next question here. So this one involves temperature, right? So we looked at tides. This one's involving temperature. So the average monthly temperature for October 2007, from October 2007 to October 2008, for Scotland are shown in this table below. Give a sinusoidal model, so that equation, using 31 as the minimum and 66 as the maximum, right? So here we're just writing this model. So I'm using this as my maximum, minimum, this is my maximum. So my independent variable is the month that it's happening in, and my dependent variable is the actual temperature. So from here to here, like I'm starting at the minimum, going up to the maximum, and coming back down. So just based off of that information, so like this is 331, this is 966, right? So you can imagine that over here, well, I want 6 and then 6 more. What's this going to be? 1531. So I'm going to go ahead and let's see. So it's going to be negative. Let's come back to that. Cosine. Well, the period, so from 3 to 15 is 12, right? 12 months. So the way I'm going to have, so it would be 2 pi over the period, which is where I'll go ahead and get pi over 6. I'm using this as my starting point, right? My phase shift. So I would have x minus 3. X is the months. And then plus the sinusoidal axis. So then I just need to calculate this, right? So the middle of these, well, what's halfway between 31 and 66? 66 and 31 is 97, and half of that is 48.5, right? 48.5? Yeah, sorry. So my sinusoidal axis would be at 48.5. My amplitude then, I want to know, so this is y equals 48.5. To get from there to the top, or there to the bottom, right, I just need to go ahead and say, well, 66 minus 48.5. And whatever that is, and that's one way to do it. I could also find the range and then do half of the range. Okay, that's also what the amplitude is. So that's where I've got 17.5 or 35 halves. So I've got negative 17.5 cosine of pi over 6 x minus 3 plus 48.5. Right, so that's me using this minimum as my starting point, as my phase shift, right? Maybe I used 6. Oh, it's a quarter. Different as my starting point. So I'd be starting right here, right? This point right here would be 6, actually 17.5. No, sorry, 48.5. Right? So I could do it that way too, and I could have another model that is y equals negative 17.5. Nope, it would be positive 17.5 in this case. 17.5 sine of, it's still going to have a period, a b value of pi over 6, still has a period of 12, x minus 6, but the sinusoidal axis is still 48.5. Right? And you could go ahead and let's say I wanted to graph these, to look at them. Let's put both of these in there so I can show you what it looks like. So negative 17.5 cosine of pi over 6 x minus 3 plus 48.5, and then negative 17.5 sine of pi over 6. It's always good to practice with using your calculator and calculator keystrokes. So this can never hurt, guys. Plus 48.5. And I'm going to go ahead and change the window before I even graph it. So I know that my x is going to go from, I'll go from like 0 to, I'll go to 24. So we can see a few cycles. Oh no, window, sorry. This, I'll make it go from 30 to 80. And I'm going to go ahead and actually, in y equals, I want you to, and then I'm going to actually change the mode so they graph at the same time. I think that should work. And I'll go ahead and graph it. Can you not see the other one because they're exactly the same? Is that what my issue is? Maybe I don't want them to graph at the same time. I want it to be sequential. Can you see the blue? Apparently not. Right, so there's one of them. You can't really see the blue one. I'll turn that one off. Did I make a mistake in the blue one, guys? Negative 17.5 cosine. No, I forgot a parenthesis. There we go. Let's turn them both on again. No! Okay. Okay. Well, you saw that they were the same. It was rather upsetting. Well, I'm gonna quit my screen. We're gonna move on. But you can always try to write another model for it, right? That's a great practice, but like I'm just shifting it. Like I could have started at 9. I could have started at 12, right? Like you could start at those, that shift of a quarter, like a quarter of a circle is gonna change it from sine to cosine. Like what's the best fit model? So you can play around with that. And let's take a look at this last one that we're gonna do together, a pendulum. So a pendulum is swinging. There's this little picture here. So it's swinging. And it swings to a maximum height of 23 centimeters from the ground and it achieves a minimum of 5 centimeters. So right away, 5 to 23, right? So I'm sorry, yeah, 5 to 23, that's going to be the range. So my range would be 18. So I actually know that right away my amplitude is 9, right? Cool. I'm just going to write it down as I think about it. If a full swing occurs in 3 seconds, all right, so the period is 3 seconds. And the pendulum is released from its maximum height, right? So it's going from its maximum height to its minimum height, back to its maximum height. This is not what it looks like when it swings. Like this is us measuring, or I guess comparing the time, right? So if I were to graph it, the time since it was dropped, like since it started, to its height, right? It's like when a pendulum is swinging, it's like if I drop it from here, it's going to swing and then swing back, right? Like that's the idea of it. That's one full cycle of it. So how high will it be after 26 seconds? So let's go ahead and let's write a model of this. So we already know the amplitude, y equals 9 cosine. The period is 3, so I would have my b value would be 2 pi over 3, x, just x, right? Like there's no phase shift that's happening here. It's just right at the beginning at 0 seconds, it's at that height. That's where you're starting at, right? It says it's being released from its maximum height. And then I just need to figure out the midline, right? So I need to go ahead and average these. So I could go, that's 14 would be the middle, halfway between 5 and 23. So then how high will it be after 26 seconds? So what is 9 cosine of 2 pi over 3 times 26 plus 14? Right? What is 9 cosine of 2 pi over 3 times 26 plus 14? I'm just hopefully still in radians. 9.5. All right, let's also go ahead and put this in y equals 9 cosine of 2 . I'm not convinced I plugged that in right, but we're going to find out in a moment. 14. Let's change the window. So the minimum is 5, the maximum is 23. I'll just change this to 30. Oh, no. Wow. 0 to 30. And this is just 3 seconds, so I'll just go ahead and say like 10. Cool. Right, so second trace value, let's see, after 26 seconds, where it is. Oh, it's not in the window. Sorry. Ooh. Second trace value, 26. 9.5. No, I did plug it in right. Wasn't convinced for a moment. Sorry, guys. Pretty cool, right? So this next one, after how many seconds will the pendulum reach a height of 10 centimeters for the third time? I'm going to change the window because this is a little messy. So I want my X maximum. I'll go ahead and say, so Y equals, I'm going to graph 10. Oh, I forgot I didn't change that. Sorry. So it's starting at its maximum. Here it hits it once. Here it hits it twice. Here it hits it 3 times. So I want to figure out this point of intersection. So second trace, intersect, go on over. One, two, it's right here. Guess it. So what is that? 3.969, 3.97 seconds. So almost 4 seconds, right? Almost 4 seconds is when it would hit 10 centimeters for the third time, right? Because it hits it on the way down and the way up for its first cycle, and then again on the way down, right? And you can count, you can just go over to any of them, but it repeats, right? So pretty cool. Pretty cool to play around with. Practice using your calculator, playing around with it, graphing it, make sure you're paying attention to the window, and practice adjusting it and thinking about the situation that you're graphing. So in this lesson, we looked at some applications involving sinusoidal functions and did some practice finding models and making predictions and using our calculator. So I'd really encourage you to go ahead and maybe try a few problems right now or sometime in the near future for part 1 to figure out what questions you have. In the next video, I'm actually going to be doing a few more examples and then going over your part 2 homework. So it might benefit you to have that or to maybe have looked at it and even tried it and do it along with me in the next video. Thanks everyone for watching, and I will see you all soon.